There may be a place in our own solar system where alien life is hiding right now. Not in a distant galaxy, not around a star we can barely see, not on a planet so far away that its light has spent hundreds of years crossing space. Possibly much closer. Close enough that our spacecraft have already flown near it. Close enough that we have photographed its surface. Close enough that the evidence is not coming from imagination, but from ice, dust, chemistry, gravity, magnetism, and water. That is what makes this question so strange. When most people imagine alien life, they picture a signal from deep space, a civilization around another star, or something looking back at us from a world we will never reach. But the first alien life humans ever find might not be advanced. It might not build cities. It might not send messages. It might not even see sunlight. It could be microscopic. It could be buried. It could be sealed below kilometers of ice, floating in a dark ocean that has never known a sunrise. And if that is true, then one of the biggest discoveries in human history may be waiting not across the universe, but inside the worlds orbiting the same sun as Earth. Before we begin, if you enjoy calm space documentaries like this, subscribe to channel, leave a like, and write a comment telling us where you are watching from and what time it is where you are right now. It is always strange to remember that while one person is watching this at midnight, another may be hearing the same story at sunrise, somewhere else on the same small planet. Tonight, you are watching the Space for Sleep channel, talking about the closest place alien life could be hiding. And to understand where alien life might be closest, we have to begin with a question that sounds simple, but is not simple at all. What are we actually searching for? Because when we say alien life, the mind tends to jump too far too quickly. It imagines creatures, movement, eyes, machines, maybe entire worlds covered in strange forests or oceans filled with unfamiliar animals. But science usually begins with something much smaller and much quieter. It begins with chemistry that can copy itself. It begins with molecules that do not merely exist, but organize, react, consume energy, and preserve information. Life, at least the only kind we know, is not made from magic ingredients. It is made from atoms that are common across the universe: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. The same basic pieces appear in stars, comets, meteorites, icy moons, planets, nebulae, and interstellar clouds. The ingredients are not rare. The mystery is not whether the universe can make the building blocks. The mystery is whether those building blocks can assemble into something alive somewhere else. On Earth, life seems deeply connected to liquid water. Every living thing we know uses water in some way. Water is not just something life drinks. It is the medium where chemistry happens. It carries dissolved materials. It allows molecules to move, meet, break apart, recombine, and build structures that would be almost impossible in dry stone or frozen gas. This is why the search for alien life often follows water. Not because water guarantees life, not because every ocean must be alive, but because, if you are searching in darkness, you begin where the lamp is strongest. For many years, that made scientists look mostly for planets like Earth, rocky worlds in the habitable zone, not too close to their star, not too far, warm enough for oceans, cool enough that water does not simply boil away, a surface where sunlight, atmosphere, geology, and chemistry might work together for billions of years. Earth is our example, so Earth became the pattern. But the more we explored our own solar system, the more that pattern began to change. We learned that liquid water does not always need sunlight. We learned that oceans can hide below ice. We learned that moons can be warmed from the inside by gravity itself. We learned that a world can look frozen, dead, and silent on the surface, while still holding a possible habitat underneath. That is the key to this whole story. The closest place alien life could be hiding may not be a planet at all. It may be a moon. Or it may be under the ground of a planet that looks empty from above. Or it may be in a place that does not resemble Earth on the outside, but resembles part of Earth, deep below. Because Earth has already taught us that life is not always where sunlight is. In the deep ocean, far below the reach of daylight, entire ecosystems live around hydrothermal vents. There, water heated by Earth's interior flows out of cracks in the seafloor, carrying minerals and chemical energy. Organisms do not rely on sunlight directly. They rely on chemistry. Microbes convert chemical energy into biological energy, and larger organisms depend on those microbes. This changed how scientists thought about habitability. If life can survive in darkness on Earth, powered by chemical reactions near the seafloor, then a hidden ocean on another world does not need blue skies. It does not need beaches. It does not need plants. It does not even need a visible surface. It needs liquid water. It needs chemistry. It needs energy. It needs enough time. And the solar system contains several places that might satisfy those conditions. But there is another rule we have to keep in mind. Possible is not the same as proven. So far, no life has been confirmed beyond Earth. Not on Mars, not on Europa, not on Enceladus, not in the clouds of Venus, not in any meteorite, not in any radio signal. The universe has given us hints, environments, chemistry, and reasons to keep looking. But it has not yet given us a confirmed second biology. That makes the search more powerful, not less. Because if we ever find even a single microbe that began independently from life on Earth, then biology stops being a one-world accident. It becomes something the universe can do more than once. The meaning would be enormous. If life appeared twice in one small solar system, then life may be common in the galaxy. If life appeared on Earth and also under the ice of a moon around Jupiter or Saturn, then the silence of the stars would feel different. The universe would still be vast, but it would no longer feel biologically empty. So where do we look first? The closest possible answer begins with Mars. Mars is the world that has haunted human imagination longer than any other candidate. It is close enough to appear red in the night sky. Close enough for telescopes to reveal markings that people once mistook for canals. Close enough that we have sent orbiters, landers, and rovers again and again. Mars is not the most promising place in every way, but it is the closest world that once looked surprisingly Earth-like. Today, Mars is cold, dry, and harsh. Its atmosphere is thin, mostly carbon dioxide, and far too weak to protect the surface properly. Liquid water cannot remain stable for long under normal surface conditions. Radiation from space reaches the ground more easily than it does on Earth. The soil is chemically hostile. The air is so thin that if you stood there unprotected, the problem would not be whether you could breathe comfortably. You could not breathe at all. And yet, Mars was not always like this. Its surface is covered with old evidence of moving water. River valleys, ancient lake beds, deltas, minerals that form in wet environments, channels carved across landscapes that now sit under a thin orange sky. At some point in the deep past, Mars had liquid water on its surface. It had places where water gathered and flowed. It may have had a thicker atmosphere. It may have been warmer. And for a period of time, it may have had the kinds of environments where microbes could have lived. That is the first reason Mars matters. The question is not only whether life exists there now, the question is whether life ever began there. If it did, then the next question becomes even more difficult. Could any of it have survived? Surface Mars is brutal today, but life on Earth is not always on the surface. Microbes live underground. They live inside rocks. They survive in deserts, ice, salt, radiation, acidic pools, deep crustal environments, and places that seem almost impossible from a human point of view. A microbe does not need a blue sky. It does not need sunlight if it can use chemical energy. It does not need comfort. It only needs a stable niche where its chemistry can keep going. That is why Mars remains so important. If there is life there now, the best chance may not be on the open surface. It may be underground, where radiation is weaker, temperature changes are smaller, and water, ice, or briny liquid might exist in protected spaces. Mars may be dead on the outside and not completely dead below. But Mars also has a problem. It is not enough to say that Mars once had water. Earth also has places where water once flowed, and life is gone now. A habitable environment is not the same as an inhabited one. Mars may have been warm and wet enough for chemistry, but not long enough for life to begin. Or life may have begun, only to disappear when the planet lost its atmosphere, its magnetic shield, and much of its surface water. There is also the issue of evidence. If ancient life existed on Mars billions of years ago, its remains may be fragile, altered, buried, or destroyed. Surface radiation breaks down organic molecules over time. Dust covers old rocks. Geological processes can hide or confuse the story. That is why rovers look carefully at ancient lake beds and sedimentary rocks. Sediments can preserve history. On Earth, mud and minerals can trap signs of past environments. They can hold organic molecules. They can record whether water was present, whether the chemistry was friendly, and whether the conditions lasted long enough to matter. Mars rovers have not found confirmed life, but they have found a planet that was once more habitable than the Mars we see today. That distinction matters. Mars is not just a red desert. It is a world with a buried memory. Imagine standing at the edge of an ancient Martian river delta. The air today is thin and freezing. The sky is dusty. No trees move. No birds call. No water shines. But billions of years ago, water may have entered a lake there, carrying mud, minerals, and chemical ingredients into still basins. On Earth, places like that can preserve life. On Mars, places like that may preserve a question. This makes Mars emotionally powerful, because it is close and almost familiar. It has sunsets, it has valleys, it has polar caps, it has dust storms and mountains and canyons. It feels like a place that could once have been something more. But if we are asking where alien life could be hiding now, Mars may not be the strongest candidate. For that, we have to go farther from the Sun. That sounds wrong at first. The farther you travel from the Sun, the colder the solar system becomes. Sunlight weakens, worlds freeze, surfaces harden. The warmth that makes Earth comfortable fades into a distant glow. You might expect life to become less likely. But in the outer solar system, something surprising happens. The most interesting places are not warm because of sunlight. They are warmed by gravity. A moon orbiting a giant planet can be squeezed and flexed by tidal forces. As it moves through the gravitational field of its planet and as nearby moons tug on it, its interior can stretch and relax over and over again. That mechanical distortion creates heat. It is not sunlight from above. It is friction from within. This is why a small moon can stay active far from the Sun. It is why Io, Jupiter's volcanic moon, is covered with eruptions. It is why Europa may hide a global ocean under ice. It is why Enceladus, tiny and frozen, can spray water into space. The outer solar system is not simply a cemetery of ice. It is a place where gravity does quiet work. And that brings us to Europa. Europa orbits Jupiter, the largest planet in the solar system. From a distance, it looks like a bright, icy sphere marked by long cracks, reddish lines, and strange, disrupted regions. It is smaller than Earth's moon, but its surface is one of the most fascinating landscapes ever photographed. It does not look alive. It looks frozen. It looks sealed. It looks like a world where everything has been locked away. But that may be exactly why it matters. Beneath Europa's icy crust, scientists think there may be a global ocean. Not a small pocket of water. Not a temporary melt zone. A vast ocean that could contain more water than all of Earth's oceans combined. That idea did not come from a single photograph. It came from a collection of clues. Europa's surface is unusually smooth compared with many other moons. It has fewer large craters than expected, suggesting the surface may be geologically young and renewed over time. Its long cracks and ridges hint that the ice shell has moved, fractured, and shifted. Some regions look as if blocks of ice once broke apart and drifted, almost like icebergs frozen back into place. Then, there was the magnetic evidence. The Galileo spacecraft, which studied Jupiter and its moons in the 1990s and early 2000s, found signs that Europa responds to Jupiter's magnetic field in a way consistent with a conducting layer beneath the surface. Salty liquid water can conduct electricity. A global salty ocean would fit the observation. This does not prove life, but it makes Europa one of the strongest candidates for habitability in the solar system. Because Europa may have the first ingredient, liquid water. It may have the second ingredient, chemistry from rock and ocean interaction below. It may have the third ingredient, energy from tidal heating. And it may have had these conditions for a very long time. The most important part of Europa may not be the ice. It may be the seafloor. If Europa's ocean touches a rocky mantle beneath it, then water and rock may interact chemically. On Earth, water-rock reactions can create chemical gradients. They can release hydrogen. They can support ecosystems around hydrothermal vents. They can provide energy even when sunlight is absent. So the dream of Europa is not that fish are swimming under the ice. That is not where serious science begins. The more careful question is whether microbes could live in a dark ocean using chemical energy near the seafloor. If they can, then Europa could be alive without looking alive. That is the terrifying beauty of it. A moon can orbit Jupiter for billions of years, covered by ice, bombarded by radiation, shining silently in the darkness, and still have an ocean below where chemistry continues. From outside, you would see almost nothing. No green continents, no clouds of oxygen-rich air, no lights, no obvious signal, only ice, cracks, and the distant glare of Jupiter. But below that surface, the real story may be hidden. Europa also teaches us something important about the word closest. Mars is closer in distance, but the closest place where life could be hiding does not only mean the nearest place to Earth, it can also mean the nearest place where the conditions still look seriously promising. Mars may be closer as a destination. Europa may be closer to the kind of protected habitat life needs now. But Europa is hard to reach and even harder to investigate. The surface is dangerous. Jupiter's radiation environment is intense. A spacecraft near Europa must survive charged particles trapped in Jupiter's powerful magnetosphere. The ice shell may be many kilometers thick. Even if an ocean lies below, reaching it directly is far beyond anything we have done. Imagine landing on a frozen world, then trying to drill through miles of ice while operating far from Earth in extreme cold, under radiation, with limited power and no possibility of repair. This is why Europa is both exciting and frustrating. It may hold one of the best nearby habitats, but it keeps that habitat hidden behind a locked door. That is also why missions like Europa Clipper matter. Europa Clipper is not designed to land and drill into the ocean. Its job is to study Europa from repeated flybys, mapping the surface, analyzing composition, measuring ice thickness clues, investigating the ocean evidence, and asking whether Europa has environments that could support life. That wording is careful. support life, not detect life directly, not prove alien organisms exist, not return a sample from the ocean. The first step is to understand the world well enough to know where future missions should look. This is how planetary science often works. It does not usually leap from mystery to answer. It moves from suspicion to evidence, from evidence to mission, from mission to better questions. Europa may be one of the greatest questions we have ever orbited. But it is not alone. Farther out, around Saturn, there is another world that changed the entire search for life. A small moon that should have been quiet. A frozen body only about 500 kilometers wide. A place that could easily have been dismissed as just another icy object among many. Then, it began spraying its interior into space. Enceladus is one of the strangest gifts the solar system has ever given to astrobiology. Unlike Europa, which hides its ocean under ice, Enceladus appears to let part of its hidden ocean escape. Near its south pole, long fractures known as tiger stripes cut across the surface. From those cracks, jets of water vapor and ice particles erupt into space, forming a plume that feeds Saturn's E-ring. This is an astonishing fact. A moon in the outer solar system is venting material from inside itself into space, where a spacecraft can fly through it. That means Enceladus is not only interesting because it may have an ocean. It is interesting because it may be sampling itself for us. NASA's Cassini spacecraft flew through the plume and detected water vapor, salts, organic molecules, and evidence of chemical energy. It did not find life, but it found signs that Enceladus has several ingredients scientists care about when asking whether a place could be habitable. Liquid water, organic chemistry, energy, interaction between water and rock. Those four ideas changed the status of Enceladus. It was no longer just a beautiful icy moon. It became one of the closest possible windows into an alien ocean. Think about the difference between Europa and Enceladus. Europa may have a larger ocean. Europa may be one of the most important ocean worlds in the solar system. But Europa's ocean is hidden below thick ice. Enceladus may be smaller, but it is leaking. And in astrobiology, leaking matters. If a world throws ocean material into space, then a future mission might not need to land and drill. It might fly through the plume, collect particles, analyze molecules, and search for patterns that could tell us whether the ocean below is merely chemically interesting or something more. This is why many scientists consider Enceladus one of the most promising targets in the search for life. It offers access. Not easy access. Nothing in deep space is easy. But compared with drilling through kilometers of ice, flying through a plume is a remarkable opportunity. The idea is almost unreal. A spacecraft could pass through a spray of frozen ocean droplets far from the sun, around Saturn. And inside those tiny particles might be information about a hidden sea that has never been seen directly. Maybe just salts, maybe complex organic chemistry, maybe evidence of hydrothermal activity. Maybe, someday, if nature has been kind and instruments are sensitive enough, something that looks like biology. This is where the search becomes delicate. Organic molecules do not mean life. That point is important. Organic chemistry can happen without biology. Carbon-based molecules can form through non-living processes. Comets contain organics. Meteorites carry organics. Interstellar clouds contain complex molecules. Chemistry is creative even when nothing is alive. So finding organics is not the same as finding organisms. But organics in the presence of liquid water and energy are worth paying attention to. They mean the environment is not chemically empty. They mean the ingredients are there. They mean the question becomes sharper. Could the ocean of Enceladus host life? We do not know. And that uncertainty is more powerful than a simple yes or no. Because Enceladus forces us to imagine a kind of alien life that would be hidden from every ordinary sense. No forests, no continents, no sky, no surface weather in the way we understand it. Just a dark ocean below ice, perhaps touching warm rock, perhaps stirred by chemistry, perhaps existing for millions or billions of years. If microbes live there, they may not know the universe exists. They may never see Saturn hanging above them. They may never experience sunlight. They may live and die inside water, trapped under a shell of ice, while above them, their moon shines coldly in the black. That is one of the strangest possibilities in all of science. Life may not need to be aware of the stars to belong to the universe. Still, before we let the imagination go too far, we have to return to the evidence. Cassini gave us a strong reason to care about Enceladus. But Cassini was not built as a life detection mission. It was an extraordinary spacecraft, but it was designed before we fully understood how important Enceladus would become. It could analyze plume material, but it could not answer every biological question. Future missions would need instruments designed specifically for this search. They would need to distinguish between abiotic chemistry and possible biological patterns. They would need to measure molecules carefully. They would need to understand contamination risks. They would need to know whether complex organics, isotopic ratios, cell-like structures, or other biosignatures point toward life or toward non-living chemistry. This is not easy. Searching for life is not like searching for a rock. A rock can be photographed, weighed, mapped, and named. Life is a process. It can be subtle. It can leave ambiguous traces. It can be confused with chemistry. And if alien life is very different from Earth life, our assumptions may fail. That is why the closest place alien life could be hiding is not just a location. It is a scientific challenge. We have to know what to look for. We have to avoid fooling ourselves. We have to recognize that the first sign may not be dramatic. There may be no creature swimming past a camera. There may be no clear cell under a microscope. There may be only ratios, molecules, patterns, and an argument strong enough to change history. But even that would be extraordinary. Imagine a future spacecraft returning data from Enceladus. It flies through a plume. It captures ice grains. It analyzes chemistry. Then, scientists notice something that does not fit ordinary geology. Not proof at first. A pattern, a strange enrichment, a set of molecules arranged in a way that suggests selection rather than randomness. The world would not instantly agree. There would be caution, debate, papers, criticism, replication, and years of analysis. That is how science works, when the claim is enormous. But somewhere in that long process, humanity might reach a point where the simplest explanation is no longer just chemistry. The simplest explanation may be life. And if that happened, the entire map of our existence would change. Not because we found aliens with cities, not because they contacted us, not because a signal arrived from another star, because a tiny moon around Saturn would prove that Earth is not the only place where matter became alive. That would make the universe feel less empty, and at the same time, more mysterious, because then the question would become bigger. If life exists twice in one solar system, how many times has it happened across the galaxy? Now, to understand why Enceladus and Europa are so important, we have to look at what makes Earth life possible in the first place. Earth is not alive just because it is warm. Venus is warm, and it is a furnace. Mars is cold, and it may have once been more friendly. Europa is frozen, yet may hold an ocean. Enceladus is tiny, yet vents water into space. Habitability is not a single number. It is a system. Temperature matters, but so does pressure. Water matters, but so does chemistry. Energy matters, but too much energy can destroy what it might otherwise power. Stability matters, But change can also create useful chemical gradients. Life does not simply require comfort. It requires usable imbalance. On Earth, life survives by taking advantage of differences: light and dark, hot and cold, oxidized and reduced chemicals, nutrient-rich and nutrient-poor zones, energy flowing from one form to another. A perfectly uniform environment may be less useful than one with gradients. This is why hydrothermal vents are so important as an analogy. At the seafloor, hot fluid rises into cold ocean water. Minerals precipitate. Chemical differences form. Energy becomes available. Microbes can exploit those differences. Ecosystems build upward from chemistry. If something similar happens on Enceladus or Europa, then sunlight is not required. What matters is whether water meets rock, whether chemistry creates energy, whether organic molecules are available, and whether the environment lasts long enough for complexity to emerge. The time factor is often forgotten. A place can have liquid water briefly and still never develop life. A place can have energy violently and destroy delicate chemistry. A place can have organics but no stable environment. Life may require not just ingredients, but patience. Earth took time. The planet formed about 4.5 billion years ago. The earliest evidence of life is still debated in detail, but life appeared early enough to suggest that once Earth became habitable, biology may not have waited forever. That is encouraging, but it does not tell us whether life is easy or rare. We only have one confirmed example. That is the great statistical problem. One living world tells us life is possible. It does not tell us how often possible becomes real. Finding a second example nearby would be like lighting a second candle in a dark room. With one candle, you cannot tell whether fire is rare. With two candles, you begin to suspect the room can burn. That is why the closest alien life matters so much. It would not only answer a local question, it would reshape our estimate of the entire galaxy. But there is a complication that makes the closest places scientifically dangerous. Earth may have contaminated them. Spacecraft are cleaned carefully, especially when they are sent to worlds that could be habitable. Planetary protection exists for a reason. If we accidentally carry Earth microbes to Mars, Europa, or Enceladus, we might confuse future searches or harm an alien ecosystem before we even know it exists. The risk is not science fiction. Earth microbes are tough. Some can survive harsh conditions, dormancy, radiation, vacuum exposure for limited periods, extreme cold, and dryness. Not all would survive a journey through space or a landing on another world, but some are resilient enough that contamination has to be taken seriously. That creates an uncomfortable situation. We want to search closely. We need to send machines. But the more closely we investigate, the more careful we must be not to bring our own biology with us. The search for alien life is also a search for restraint. This is especially important for ocean worlds. If Europa or Enceladus has a habitable ocean, then future missions must avoid introducing Earth organisms into that environment. A lander, penetrator, cryobot, or sample system would need extreme sterilization. Even flying through a plume requires careful design so that collected material is interpreted correctly. A false positive would be devastating. Imagine announcing alien life, then learning the signal came from contamination. A false negative would also be painful. Imagine missing life because our instruments were not sensitive enough, or because we looked for the wrong kind of biosignature. This is why the search moves slowly. It can feel frustrating from the outside. People want a simple answer: is there life or not? But the universe rarely gives answers in the format we prefer. Instead, it gives environments. It gives hints. It gives chemistry. It gives strange worlds and asks us to become better at asking questions. So far, The strongest nearby candidates form a kind of ladder. Mars is the closest major world with an ancient habitable past and possible subsurface refuges. Europa is a large icy moon with strong evidence for a hidden global ocean. Enceladus is a small icy moon that actively sprays ocean material into space. Titan, which we will reach later, is different again, with organic chemistry and methane seas. Venus, surprisingly, has clouds that some have considered in terms of habitability, though its surface is almost unimaginably hostile. Each place offers a different version of the same question. How flexible is life? Can it begin on a planet that later becomes a desert? Can it survive under ice far from sunlight? Can it use chemistry in an ocean that has never seen the sky? Can it exist in solvents other than water? Can it persist in clouds above a hellish surface? The answer may be no in most places. That is possible. The solar system might be mostly sterile, with Earth as a rare exception. Mars may have been habitable but lifeless. Europa may have an ocean but no biology. Enceladus may have chemistry but no organisms. Titan may be complex but not alive. That would be profound too. A sterile solar system would tell us that life is harder than habitability. It would mean the ingredients can gather, the water can flow, the energy can exist, and still biology may not appear. That would make Earth feel even stranger. But if even one of these worlds is alive, then everything changes. And the closest realistic places are close enough that we can imagine reaching them with machines. That is what separates this question from distant exoplanets. Exoplanets are fascinating. Some may be Earth-sized. Some orbit in habitable zones. Some may have atmospheres we can study with telescopes. But they are still incredibly far away. Even the nearest known exoplanet system, Proxima Centauri, is more than 4 light-years from Earth. A spacecraft traveling at the speed of Voyager would take tens of thousands of years to get there. We cannot yet touch them. Mars, Europa, Enceladus, and Titan are different. They are distant by human standards, but reachable by robotic exploration. We have already landed on Mars. We have already orbited Saturn. We have already flown through Enceladus's plume. We have already mapped Europa from spacecraft. We have sent a probe through Titan's atmosphere and placed it on the surface. The closest alien life may be close enough not for humans to visit tomorrow, but for instruments to investigate within a few mission generations. That is the suspense of the next century. We may not need to wait for a radio signal. We may need to wait for a sample, a plume fly-through, a drill, a lander, or a laboratory instrument far from Earth. But before deciding which world is the strongest candidate, we need to spend more time with each one. Mars gives us the story of lost habitability. Europa gives us the story of a hidden ocean. Enceladus gives us the story of accessible ocean material. Titan gives us the story of chemistry pushed in a completely different direction. Venus gives us the story of a planet that looks dead below, but may still raise questions above. But there is a deeper reason these nearby worlds are so hard to judge. They are not frozen in one simple state. They have histories. A planet, or moon, can be more habitable in one era than another. Mars may have been better billions of years ago. Europa may be more stable today than its surface suggests. Enceladus may have become active in ways we are still trying to understand. Titan may preserve chemistry that is not alive, but still resembles some of the ingredients that once existed on early Earth. This means the search for alien life is also a search through time. We are not only asking what a place is now, we are asking what it used to be, what it may become, and whether life had a window long enough to begin. Mars is the clearest example. If a rover finds organic molecules in an ancient mudstone, that does not automatically mean life was there. Organics can arrive from meteorites. They can form through geology, they can be preserved, without biology. But if those molecules appear in a rock that formed in water, in an environment with the right chemistry, at a time when Mars had rivers and lakes, then the question becomes harder to dismiss. The evidence builds in layers. First, was water present? Then, was it liquid for long enough? Was the chemistry friendly or destructive? Were there energy sources microbes could use? Could organic molecules survive? Could minerals preserve delicate signs? Could later radiation erase them? Every question narrows the search. This is why Mars missions often return to old lake beds, deltas, clays, sulfates, and sedimentary rocks. They are not random targets. They are archives. A lava plain might tell us about volcanism. A crater wall might expose geology. But a delta tells us that water once carried material into a basin, sorted it, deposited it, and left behind layers. Layers are memory. On Earth, layers can preserve fossils, chemical traces, ancient climates, and the slow writing of environments over time. On Mars, they may preserve the difference between a planet that was simply wet and a planet that might once have been alive. The difficulty is that Martian life, if it ever existed, was probably microbial. Microbial life does not always leave dramatic fossils. It can form mats, chemical changes, mineral patterns, isotopic signals, and tiny structures that require extreme care to interpret. Even on Earth, ancient microfossils can be debated. On Mars, where we cannot walk freely with full laboratories, the problem becomes even harder. A rover is a miracle of engineering, but it is not an entire Earth laboratory. It must carry limited instruments. It must drill only a little. It must choose targets carefully. It must work slowly, with commands sent across millions of kilometers. It must survive dust, cold, aging parts, and the silence between transmissions. This is why sample return has been considered so important. A rock on Mars can be studied by a rover, but a rock returned to Earth could be studied by generations of instruments, with techniques that do not fit on a spacecraft, by scientists who can repeat, refine, and challenge each result. Still, Mars has one disadvantage compared with Europa and Enceladus. Its ancient habitable environments may be gone. If life never began there, then Mars is a museum of failed habitability. If life began and died out, then Mars is a graveyard. If life began and retreated underground, then Mars is a hiding place. Those are three very different stories, and the surface alone may not tell us which one is true. This is where the icy moons become so tempting. They may not preserve a lost ocean. They may contain an ocean right now. Europa, for example, is not interesting only because it once had water. It is interesting because its ocean may still exist beneath the ice. That changes the emotional weight of the question. We are not only looking for ancient remains, we may be looking for an active environment. An active ocean means chemistry can still happen. It means heat can still move. It means materials can still circulate. It means if life ever started, it might still have a place to continue. But Europa also forces us to confront a strange kind of blindness. We can photograph the surface. We can measure the magnetic response. We can study the cracks and colors. We can model the tides. But the ocean itself remains unseen. Imagine trying to understand Earth's oceans from space if the entire planet were covered in ice. You might see fractures. You might detect gravity signals. You might infer movement. You might notice regions where the ice looked disrupted. But the living ocean below would be hidden from your camera. That is our problem with Europa. The surface may be a message from the ocean, but it is written in ice. Some of Europa's reddish-brown streaks may contain salts or sulfur compounds altered by radiation. Some surface materials may have been brought up from below or implanted from Jupiter's environment or transformed by charged particles. Every color and crack has more than one possible explanation. This makes Europa scientifically rich, but also difficult. The Moon does not hand us a simple answer. It gives us clues that require context. The radiation environment around Jupiter adds another complication. Europa's surface is constantly processed by energetic particles. Those particles can alter chemicals, break molecules apart, and create new compounds. That means the surface may not perfectly represent the ocean beneath it. If ocean material reaches the surface, radiation may change it before we study it. So a future lander would need to know where to touch down, how deep to sample, and how to avoid mistaking radiation chemistry for ocean chemistry. This is why cracks, ridges, and young surface regions matter. If there are places where material from below has recently reached the surface, those regions may offer fresher evidence. If Europa has occasional plumes, as some observations have suggested, but not settled with the same clarity as Enceladus, then a spacecraft might sample material without landing. But uncertainty remains. Europa is promising partly because it is difficult. It asks us to solve a puzzle with many locks. Enceladus is different. Its plume makes it feel almost generous. There is something haunting about that. A moon, only a fraction of Earth's moon in size, orbiting Saturn far from the warmth of the inner solar system, is actively throwing pieces of its interior into space. It is as if a sealed world has opened a narrow window, not for us, but by its own internal physics. Cassini flew through that window. The spacecraft did not need to drill, it did not need to land, it did not need to break the ice. It passed through material that Enceladus had already released. From those encounters, scientists learned that the plume contains water vapor and icy grains. They found salts, suggesting contact with a salty liquid reservoir. They found organic molecules. They found molecular hydrogen, which is especially interesting because hydrogen can provide chemical energy for microbes in some Earth environments. Again, none of this proves life, but it means Enceladus is not simply wet. It may be chemically active. That is a crucial difference. A bottle of pure water floating in space would not be a good habitat by itself. Life needs a way to get energy. It needs chemical disequilibrium. It needs materials to build with. It needs an environment that does not instantly destroy complexity. Enceladus may have more of those pieces than anyone expected before Cassini. Its small size makes that even more surprising. Small worlds usually cool quickly. They lose heat. They become geologically quiet. Their interiors freeze. That is why Enceladus should have been easy to ignore. By size alone, it did not look like a place that could maintain a subsurface ocean. But Saturn's gravity and orbital interactions changed the story. Tidal forces can keep small worlds alive. In a geological sense, they can flex interiors, maintain warmth, and open pathways between deep reservoirs and the surface. Enceladus became a reminder that size is not destiny. A small moon can still matter. In some ways, Enceladus may be the closest place alien life could be hiding in the practical sense, not because it is closest in kilometers, but because its possible habitat may be easiest to sample. That phrase matters. The closest scientifically accessible place. Mars is physically nearer. Europa may have a huge ocean, but Enceladus sends ocean-related material into space. If a future spacecraft is designed well enough, it could fly through the plume many times, at different speeds, with instruments made specifically to search for biosignatures. It could analyze amino acids, lipids or lipid-like molecules, isotopic ratios, complex organic patterns, cell-sized particles, and the chemical context around them. The goal would not be to find one magic molecule. Life is not proven by a single ingredient. It is suggested by patterns that are hard to explain without biology. On Earth, biology tends to choose certain molecules, certain handedness, certain distributions, certain ratios. Non-living chemistry can make complexity too, but often in different patterns. A life detection mission would search for combinations, not isolated surprises. That is why the question is so delicate. If an instrument finds complex organic material in Enceladus's plume, scientists would need to ask whether hydrothermal chemistry alone could make it. If it finds amino acids, they would ask about distribution and chirality. If it finds structures, they would ask whether they formed physically. If it finds isotopic signatures, they would ask whether geochemistry can mimic them. Every possible clue has to survive doubt, and because the claim would be so important, doubt would be intense. That is not a weakness of science. It is how science protects the truth from wishful thinking. The first alien life claim will not be accepted because it is exciting. It will have to be accepted because every ordinary explanation has become less convincing. This is why a calm search is better than a dramatic one. The universe is already dramatic enough. We do not need to exaggerate Enceladus. A tiny moon around Saturn may contain a hidden ocean and vent that ocean into space. That fact alone is almost unbelievable. But the search does not end with the worlds that look most promising today. There are other nearby places where the question becomes stranger. One of them is Titan. Titan is Saturn's largest moon, and it is unlike anything else in the solar system. It has a thick atmosphere, richer than that of any other moon. It has clouds. It has weather. It has dunes. It has lakes and seas on its surface, but those lakes are not water. They are methane and ethane. Titan is so cold that water ice behaves almost like rock. Its surface temperature is around -179 degrees Celsius. At that temperature, methane can flow as a liquid. It can evaporate, form clouds, rain, carve channels, and collect in lakes. Titan has a methane cycle that resembles Earth's water cycle in shape, but not in substance. This makes Titan deeply strange. If you stood there, the landscape might look almost familiar in outline. Shorelines, hazy sky, dunes, river-like channels, smooth plains. But everything would be chemically alien. The rivers would not be water. The ground would include water ice as hard as stone. The sunlight would be weak. The atmosphere would be orange with organic haze. Titan may also have a subsurface water ocean beneath its icy crust. So Titan offers two different kinds of astrobiology at once. Below, there may be a hidden water ocean, more familiar to life as we know it. On the surface, there are liquid hydrocarbons which raise a more radical question. Could life exist in a liquid other than water? Most scientists remain cautious. Water is extraordinary for life because of its chemical properties. Methane is very different. Reactions in liquid methane at Titan's temperatures would be slow. Molecules behave differently. Cell membranes, as we know them, would not work the same way. But Titan is too chemically rich to ignore. Its atmosphere produces complex organic molecules. Sunlight and energetic particles break methane and nitrogen apart, allowing new molecules to form. These settle through the atmosphere as haze and fall to the surface. Over long times, Titan may accumulate enormous amounts of organic material. This does not mean life exists there, but it makes Titan a natural laboratory for prebiotic chemistry, the kind of chemistry that may resemble steps toward life, even if it never crosses the line into biology. Titan may show us how far chemistry can go without becoming alive. That is just as important as finding life, because to understand life, we also have to understand the boundary before life. Where does chemistry stop being ordinary chemistry? When does a system begin to store information, replicate, adapt, and evolve? What environments push molecules toward that boundary? What environments create complexity but never cross it? Titan may be one of the best places to ask those questions. And it is close enough that we are going there again. NASA's Dragonfly mission is designed to send a rotorcraft lander to Titan. It will fly from place to place in Titan's thick atmosphere, studying chemistry, surface materials, and environments that may reveal how complex organic chemistry develops on a cold world. Dragonfly is not going to find cities or animals. It is not a mission built on fantasy. It is a mission into chemical possibility. Titan widens the meaning of the search. Mars asks whether life once lived on a planet that lost its habitability. Europa asks whether life can exist in a hidden ocean under ice. Enceladus asks whether we can sample an alien ocean from space. Titan asks whether the steps toward life can happen in a world that is both familiar and completely alien. All four are close by cosmic standards. That is the shocking part. We do not need to cross the galaxy to find serious candidates. We do not even need to leave the solar system. The Sun's own family contains dead deserts, hidden oceans, methane lakes, volcanic moons, frozen surfaces, ancient riverbeds, salty plumes, and chemistry that seems to keep asking the same quiet question. Did life happen only here? Or has it been hiding nearby the whole time? That question is not answered by distance alone. If we rank by closeness to Earth, Mars comes first. If we rank by current ocean habitability, Europa and Enceladus become stronger. If we rank by access to ocean material, Enceladus may become the most tempting. If we rank by exotic chemistry, Titan becomes impossible to ignore. So the title of this video has more than one answer. The closest place alien life could be hiding depends on what kind of life we mean. Past life may be hiding in Martian rocks. Present microbial life may be hiding under Martian ground, if any survived. Water-based life may be hiding beneath Europa's ice. Accessible ocean life, if it exists, may be hiding inside Enceladus's plume material. Chemical steps toward life may be hiding on Titan. The answer is not one dot on a map. It is a set of nearby doors, and we have only begun to open them. There is also a psychological reason this subject feels different from many other space questions. When we ask how large the universe is, the answer makes us feel small. When we ask how stars die, the answer makes time feel enormous. When we ask where alien life might be hiding, the answer turns the solar system into a set of closed rooms. Some of those rooms are close. Some have already been photographed. Some have been crossed by spacecraft. And still, the most important thing inside them may remain invisible. That is why this search is so suspenseful. A world does not need to look dramatic to be important. A cracked sheet of ice can matter more than a beautiful nebula. A plume of frozen grains can be more meaningful than a galaxy image. A tiny chemical imbalance inside an ocean droplet can carry more weight than a mountain range on Mars. The scale is smaller, but the question is larger. Because this is not only about finding another organism, it is about discovering whether life is a local accident or a cosmic habit. And that is why the nearest alien world may not announce itself with lights in the sky. It may wait beneath ice, dust, rock, or haze, silent enough that only patient instruments can hear the evidence. This first part has brought us from the general question of life to the major nearby suspects, and the pattern is already clear. The search is not leading us toward places that look like Earth from the outside. It is leading us toward places where Earth-like processes may be hidden in unfamiliar forms. Mars may hide its best clues underground. Europa may hide its ocean under ice. Enceladus may hide a sea below a frozen shell, while throwing tiny pieces of it into space. The closest alien life, if it exists, may be quiet. It may be small. It may live where no sunlight reaches. It may leave no mark visible from orbit. But that does not make it less important. A single living cell beyond Earth would be one of the loudest discoveries in the history of science. And as we move into the second half of this journey, the question becomes even stranger, because not every possible hiding place is an ocean beneath ice. Some worlds challenge the very definition of habitability. Some places ask whether life could use chemistry we barely understand. Some environments seem so hostile that they should end the conversation, until one detail keeps the question alive. And that is where the search begins to leave the familiar path. It begins with the world that looks least like a place where life should belong: Titan. From far away, Titan seems almost calm. It is a large orange moon wrapped in a thick atmosphere, floating around Saturn in the cold outer solar system. It does not shine with volcanic fire like Io. It does not show bright, cracked ice like Europa. It does not throw obvious jets of water into space like Enceladus. It hides itself under a permanent golden haze, as if the moon is refusing to let us look directly at its surface. And for a long time, that haze made Titan feel more like a mystery than a target. But then spacecraft began to reveal what was underneath it. Titan has rivers, it has lakes, it has seas, it has clouds and rain and weather. The strange part is that those rivers and lakes are not made of liquid water. They are made mostly of liquid methane and ethane. On Earth, methane is a gas. We burn it for energy. It leaks from swamps and pipes and geological sources. It is not something that forms oceans under an open sky. But Titan is so cold that methane behaves like water behaves here. It can evaporate, it can condense into clouds, it can fall as rain. It can carve channels through the landscape. It can collect into dark lakes near the poles. That single fact makes Titan one of the strangest places in the solar system. It is not simply a frozen rock. It is a world with active surface chemistry. But the chemistry is happening at a temperature so low that water ice is as hard as stone. Standing on Titan would be like standing on a planet where the mountains are made of frozen water. The rain is made of hydrocarbons, and the air is thick enough to carry sound through an orange twilight. The sunlight is weak. Saturn hangs in the sky, sometimes hidden by haze. The ground may contain dunes made from organic particles, shaped by winds that move through air denser than Earth's. At first, that sounds too alien for life. And that is exactly why Titan matters. Because if life exists there, it might not be life as we know it. It might not need liquid water on the surface. It might use chemistry so different that even recognizing it would be difficult. The question is not only whether Titan has life. The question is whether biology has to follow the same recipe everywhere. This is where the search becomes more dangerous scientifically. With Mars, Europa, and Enceladus, the logic is familiar. Find liquid water. Find chemistry. Find energy. Look for microbes or traces of microbes. The environment may be difficult, but the ingredients still resemble the ones we understand. Titan does not offer that comfort. Its lakes are not warm. Its surface is not friendly to water-based organisms. Chemical reactions in Titan's cold methane seas would happen slowly compared with reactions in liquid water. Molecules move with less energy. Processes that might take seconds or minutes on Earth could take far longer in Titan's deep cold. And yet, Titan is rich in organic molecules. Sunlight and charged particles strike the methane and nitrogen in its upper atmosphere. They break molecules apart and allow new ones to form. Over time, this creates a thick haze of complex organic material. Some of those particles drift downward and settle onto the surface, like a dark chemical snow. That means Titan is not chemically empty. It is covered in raw material. The question is whether that material can organize itself into anything that behaves like life. For life on Earth, one of the key steps is compartmentalization. A living cell needs a boundary. It needs a way to separate inside from outside. It needs to keep some chemicals together, exclude others, and create a tiny controlled space where reactions can happen. On Earth, cells use membranes made from molecules that work beautifully in water. But Titan's lakes are not water, so scientists have asked a strange question. Could some kind of cell-like boundary form in methane or ethane instead? That is not the same as saying Titan has life. It is not even close. It means only that Titan forces us to think more carefully about the first physical steps that life would need. If there are stable structures that can form naturally in Titan-like liquids, then Titan becomes more than a frozen curiosity. It becomes a laboratory for a different kind of habitability. And that is why Titan is important even if it turns out to be lifeless. A dead Titan would still teach us where life's limits are. A living Titan would change the meaning of biology. But Titan has another secret beneath the surface. Like several icy worlds in the outer solar system, Titan may also hide a deep internal ocean of liquid water under its crust. That means Titan could be two very different astrobiology targets at once. On the surface, it has methane lakes and exotic organic chemistry. Deep below, it may have a more familiar water-rich environment, separated from the cold sky by layers of ice. This makes Titan difficult to classify. It is not simply an Earth-like candidate. It is not simply a weird hydrocarbon world. It may be both. And because of that, the search for life on Titan requires a different kind of patience. A rover on Mars can drill. A future spacecraft near Enceladus could fly through a plume. Europa Clipper can repeatedly pass over Europa and measure its ice, chemistry, gravity, and magnetic environment. Titan requires a mission that can move through haze, land in strange terrain, and explore chemistry at the surface. That is why Dragonfly is so exciting. Dragonfly is not a rover. It is a rotorcraft mission designed to fly through Titan's thick air and land in different places. Titan's dense atmosphere and low gravity make flying easier than it would be on many other worlds. The mission will not search for little animals or forests, or anything dramatic like that. It will study prebiotic chemistry, surface materials, and the kinds of processes that may have happened on early Earth before life began. This matters because the closest alien life may not be found by only looking for finished biology. Sometimes, the first thing we need to find is the chemistry that leads toward biology. Titan may be showing us a world where the ingredients are being processed slowly, under conditions that feel impossible from an Earth perspective. If life never starts there, the reasons will teach us something. If life does start there, the discovery would be almost beyond imagination, because it would suggest that life is not tied to one liquid, one temperature range, one familiar planet, or one exact path. It would mean the universe has more than one way to make something alive. But Titan is not the only place that complicates the search. There are worlds much closer to the Sun that have also tempted scientists, even when they appear hostile. Venus is one of them. At first, Venus seems like the wrong answer to almost every life question. The surface is hot enough to melt lead. The pressure is crushing. The atmosphere is dominated by carbon dioxide, and clouds of sulfuric acid hang above a landscape hidden from ordinary view. Venus is often called Earth's twin because of its size, but that nickname can be misleading. In terms of habitability today, Venus is more like a warning than a sibling. And yet, the conversation about Venus has never fully died. Not because the surface is friendly. It is not. The discussion survives because high above the ground, in the cloud layers, temperatures and pressures become less extreme. There are regions in the Venusian atmosphere where the physical conditions are closer to what some Earth microbes can tolerate. That does not mean life is there. The clouds are still chemically brutal. Sulfuric acid is destructive. Water is scarce. Any organism would need adaptations far beyond ordinary Earth life. Even detecting possible biosignatures in Venus's atmosphere is difficult, because chemistry can create misleading signals, and measurements can be debated for years. But Venus teaches an important lesson. The closest hiding place for life is not always the surface of a planet. A world can be dead at the ground and still raise questions in the air. That idea matters for exoplanets too. When we look at planets around other stars, we will often see only atmospheric clues. We will not be able to send probes. We will not know the landscape. We will search for gases, patterns, and chemical imbalances. Venus reminds us that atmospheres can be complicated, and that a signal that looks interesting is not the same as a discovery. This is one reason scientists are so cautious. They have to be. Alien life would be the biggest scientific discovery in history, but it would also be one of the easiest discoveries to misunderstand if the evidence were weak. A molecule is not automatically biology. A strange gas is not automatically a biosignature. A chemical imbalance is not automatically a living world. Nature has many ways to surprise us without being alive. That is why the strongest candidates are not the ones that merely sound exciting. They are the ones where several independent lines of evidence point in the same direction. Liquid water, organic molecules, a usable energy source, a stable environment, a way for material to move and mix, a way for future missions to test the idea. By that standard, Titan remains fascinating, Venus remains provocative, Mars remains close, Europa remains powerful, and Enceladus remains almost suspiciously convenient. Because Enceladus does something most hidden ocean worlds do not do. It shares. It does not make us drill through miles of ice before we can ask the first question. It throws samples of its interior into space. Its south polar region erupts with plumes, jets of water vapor and ice grains escaping from fractures in the crust. A spacecraft can fly through those plumes and taste material that came from below the surface. That is why Enceladus may be one of the closest places alien life could be hiding in a practical sense, even though Saturn is far away. Mars is closer in distance. Europa is a stronger ocean world in size. Titan is stranger in chemistry. But Enceladus offers access, and access changes everything. Imagine trying to study a sealed ocean on another world. If the ocean is buried under an ice shell, every measurement becomes difficult. You can measure gravity. You can measure magnetic responses. You can map cracks. You can look for surface materials that may have been carried upward. But the ocean itself remains hidden. Now imagine that same ocean is leaking into space. Suddenly the problem changes. You do not have to land first. You do not have to melt through the ice first. You can send a spacecraft through the plume, collect grains, analyze molecules, measure salts, look for organic material, and test whether the ocean has the right chemical energy. Cassini already did part of this. It was not built as a dedicated life detection spacecraft. Its instruments were not designed for the full search we would want today. And yet, during its Saturn mission, Cassini flew through Enceladus's plumes and revealed a world far more active than anyone expected. It found water vapor. It found ice grains. It found salts. It found organic molecules. It found evidence of hydrothermal activity. This last detail is especially important. On Earth, hydrothermal systems can support ecosystems without sunlight. Deep under the ocean, near vents on the seafloor, chemical energy flows from the planet's interior into water. Microbes can use that energy. Other organisms can depend on those microbes. Entire communities can exist in darkness, powered not by the sun, but by chemistry. If Enceladus has water interacting with rock beneath its ocean, then it may have one of the critical ingredients for life as we understand it. Not just water, not just organics, energy. This is where the search becomes more serious. A cold ocean alone is not enough. Liquid water can be sterile if nothing useful happens inside it. Organic molecules alone are not enough. Carbon chemistry can form in many places that are not alive. Energy alone is not enough if the environment cannot preserve complex structures. But when water, organics, and energy appear together, scientists pay attention. Enceladus appears to have all three. That does not mean Enceladus has life. It means Enceladus has crossed a threshold where the question becomes scientifically sharp. Could microbes exist there? Could they live near vents on the seafloor? Could they be carried upward by circulation in the ocean? Could fragments of their chemistry be frozen into plume grains and launched into space? Could a future spacecraft detect those fragments? Each question is difficult, but none of them is fantasy. The terrifying part is not that Enceladus looks dramatic. From a distance, it looks like a small icy moon. It is bright, pale, and quiet. It does not have the obvious violence of Jupiter or the huge storms of Neptune. It does not look like a place that should hold one of the most important secrets in the solar system. And yet, beneath that smooth ice, an ocean may be moving. This is the strange humility of astrobiology. The most important place may not be the largest. The most dramatic clue may not be visible in a telescope image. The nearest life may not announce itself with a planet-sized signal. It may be hiding in droplets. If a future mission flies through an Enceladus plume and finds a pattern that cannot be explained by ordinary chemistry, everything changes. Not because we found an alien city, not because we heard a message, but because the universe would no longer contain only one known biosphere. A second biosphere would mean life happened at least twice. That is why this question carries so much weight. If all life in the universe shares one origin, then life may be rare. Perhaps Earth was lucky. Perhaps biology is an almost impossible accident. Perhaps the conditions must be perfect, in ways we barely understand. But if life began independently on another world in our own solar system, then the meaning changes. It would suggest that when the ingredients are present, life may not be a miracle. It may be a tendency. It may be something chemistry does when given enough time. Water, energy, and a protected environment. That would not prove the galaxy is full of life, but it would make the silence of the stars feel very different. Because then the question would no longer be, did life happen only here? It would become, how often does it happen, and how far can it go? This is why the closest hiding place matters more than it seems. We often imagine alien life as something far away, orbiting another star, perhaps on a planet with blue oceans and continents under a different sun. That may exist, but it may take centuries before we can study such worlds directly. Even with powerful telescopes, exoplanets remain difficult. Their atmospheres are tiny signals next to the light of their stars. Their surfaces are usually invisible. Their oceans, if they have oceans, are beyond our reach. The solar system is different. Here, we can send machines. We can fly past moons. We can land. We can drill. We can scoop soil. We can analyze ice grains. We can measure radiation, chemistry, temperature, pressure, and minerals. The distances are still enormous by human standards, but they are reachable by spacecraft. That means the first alien life we find, if we ever find any, may not come from a radio signal or a telescope image. It may come from a sample collected by a robot in a place most people have never looked at carefully. A drill hole on Mars, a plume grain from Enceladus, an icy crack on Europa, a chemical deposit on Titan. That is the real shape of the search. It is quieter than science fiction. It is slower than a movie. It is more careful than a headline. But it is also more powerful. Because the answer would be physical. A molecule, a pattern, a cell wall, a metabolic signature, an isotope ratio, a structure too organized to be accidental, a set of evidence that survives every alternative explanation. This is what scientists mean when they talk about biosignatures. A biosignature is not simply a sign that looks interesting. It is evidence that may indicate life. But because non-living chemistry can imitate parts of biology, a true biosignature has to be tested in context. For example, oxygen in an exoplanet atmosphere might sound like life, because Earth's oxygen is produced largely by photosynthesis. But oxygen can also build up through non-biological processes under some conditions. Methane can be biological on Earth, but it can also come from geological activity. Organic molecules can be made by life, but also by chemistry, in meteorites, comets, atmospheres, and interstellar clouds. So the question is never simply, did we find one molecule? The better question is, did we find a combination of clues that makes non-biological explanations less likely? On Mars, that means looking for organics in geological context. Were they preserved in ancient mudstone? Did they form in a lake? Are they associated with minerals that protect delicate molecules? Do isotope patterns suggest biological processing? Or can ordinary chemistry explain them? On Europa, that means asking whether material on the surface comes from the ocean below. If salts, organics, or other compounds are present, did they rise through cracks? Were they altered by Jupiter's radiation? Can we connect the surface chemistry to the hidden sea? On Enceladus, that means analyzing plume grains with instruments sensitive enough to distinguish simple organics from more complex patterns. Are there molecules associated with energy gradients? Are there chemical disequilibria that could support metabolism? Are there structures that suggest compartmentalization or biological processing? On Titan, the question is even stranger. What would a biosignature look like in methane chemistry? Would it be a missing compound? An unexpected distribution of molecules? A structure that forms more efficiently than chemistry should allow? A pattern in the lakes or atmosphere that cannot be explained by weather and photochemistry? These are not easy questions, but they are the right questions, and they help explain why no serious scientist can simply point to one world and say, yes, life is there. The honest answer is more careful. There are places nearby where life could be hiding. There are places nearby where life may once have existed. There are places nearby where chemistry is still active enough to keep the question alive. But there is no confirmed alien life yet. That last sentence matters. It keeps the wonder grounded. Because if we exaggerate the evidence, we cheapen the discovery before it happens. If every organic molecule becomes alien life, then the real thing loses meaning. If every strange measurement becomes proof, then science becomes storytelling instead of investigation. The search for life has to move slowly, because the answer is too important to get wrong. And that slowness can feel frustrating. We want a clear signal. We want a photograph. We want a sample that leaves no doubt. We want the universe to answer in a way that human beings can understand immediately. But nature does not have to be convenient. It may give us ambiguous chemistry first. It may give us partial clues. It may force us to send one mission, then another, then a better one, and then perhaps a sample return. The closest alien life, if it exists, may be close enough for a spacecraft to reach and still hidden enough to avoid us for generations. That is what makes the search both exciting and unsettling. The answer may be nearby, but not easy. Mars is close, but its best evidence may be buried. Europa is promising, but protected by ice and radiation. Enceladus offers samples, but they are tiny and difficult to interpret. Titan is rich in chemistry, but it may demand a broader definition of life. Venus is close, but its environment is harsh, and its evidence uncertain. Each world gives us part of the puzzle. None gives us the full answer yet. So, which one is the closest place alien life could be hiding? The answer depends on what we mean by closest. If we mean closest in distance, Mars is the obvious candidate. It is our planetary neighbor, Spacecraft have reached it many times. Rovers have driven across its surface. Orbiters have mapped it in detail. Ancient Mars had water, lakes, rivers, deltas, and conditions that may have been suitable for microbial life. If life ever began there, its remains may still be preserved underground, shielded from radiation and oxidation. Mars is the nearest serious possibility, but if we mean closest to the right environment today, Mars becomes less certain. The present surface is cold, dry, irradiated, and chemically harsh. The best modern habitats, if they exist, are probably underground or under ice. That makes Mars accessible in distance but difficult in depth. If we mean closest to an active liquid water habitat, Europa and Enceladus become stronger candidates. Europa's ocean may be huge. Its tidal heating is powerful. Its interaction with Jupiter gives it energy and complexity. But Europa's ice shell and radiation environment make direct access challenging. Enceladus is smaller and farther away, but its plume makes the hidden ocean unusually testable. It is not just a candidate, it is a candidate that throws pieces of the evidence into space. That may make Enceladus scientifically closer than its distance suggests. If we mean closest to a second kind of life, Titan becomes impossible to ignore. It may not be the easiest place to find Earth-like biology, but it may be the place that tests whether biology can be more alien than we expected. And if we mean closest to proving that life is not unique to Earth, the answer may not be a single world at all. It may be the comparison between them. Mars tells us whether a once wet planet nearby could have started life. Europa tells us whether large hidden oceans can remain habitable far from the sun. Enceladus tells us whether a small icy moon can maintain water, organics, and energy at the same time. Titan tells us whether complex chemistry can move toward life in a completely unfamiliar environment. Venus tells us how careful we must be with atmospheric clues. Together, they form a map. Not a map of where aliens definitely are, a map of where the question is strongest. And that map points to an uncomfortable possibility. The first alien life we discover may be unimpressive to the eye. It may not glow, it may not move in a way we can see. It may not build anything. It may not communicate. It may not even live on a surface. It may be microscopic, hidden, slow, and fragile. A cell in briny water, a chemical film on a mineral surface, a metabolism near a vent, a dormant organism locked inside ice, a molecular system in a methane lake that only barely resembles what we call life. And still it would be enough. Because the discovery would not be important because the organism is impressive. It would be important because of where it is, not Earth. That difference would divide history into two parts. Before we knew life could happen elsewhere. After we knew, everything about our place in the universe would feel different after that. Right now, Earth is the only known living world. Every forest, every ocean, every insect, every human being, every fossil, every microbe in the deepest rock we have studied belongs to one connected biological story. Life here has changed forms endlessly, but it shares a common ancestry. All known life is one family. That is beautiful. It is also lonely. A second example would end that loneliness in a scientific sense. It would not tell us how common intelligent life is. It would not prove there are civilizations. It would not answer the Fermi paradox by itself. It would not tell us whether anyone else is looking back, but it would show that biology is not confined to the world that produced us. And that may be the most important first step. Before we ask where the nearest civilization is, we have to ask where the nearest cell could be. Before we search for voices in the galaxy, we have to understand whether life can begin twice in one small solar system. Because if it can, then the galaxy changes. Every icy moon, around a giant planet becomes more interesting. Every subsurface ocean becomes a possible habitat. Every quiet red dwarf system with rocky planets becomes harder to dismiss. Every exoplanet atmosphere becomes a clue in a much larger story. The search moves from hope to expectation. Not certainty, but expectation. That is why this question is so powerful. The closest alien life may not be far enough away to feel like science fiction. It may not require faster-than-light travel. It may not require crossing the galaxy. It may be inside our own solar system, waiting under a shell that sunlight never penetrates. And if that is true, then our solar system is not only a collection of planets and moons, it is a set of experiments. Earth shows one outcome. Mars shows what happens when habitability fades. Venus shows what happens when climate runs away. Europa and Enceladus show what happens when oceans hide inside ice. Titan shows what happens when organic chemistry develops in a cold alien solvent system. Each world is a different answer to the same cosmic question. What does matter do when it is given time, energy, and a place to organize? Sometimes it makes rock, sometimes it makes oceans. Sometimes it makes complex molecules, and at least once, on Earth, it made life. The terrifying possibility is that Earth may not be exceptional in the way we once imagined. The comforting possibility is the same. Because if life is common, then we are less alone. But if life is common and intelligence is rare, the silence around us becomes even stranger. A galaxy full of microbes would still be quiet. A solar system with several living oceans would still have no voices. A universe rich in biology might still contain very few minds able to know it exists. That thought is almost more haunting than loneliness. It suggests that life may appear in hidden places, persist in darkness, adapt to chemistry, and survive under ice, while intelligence remains a fragile accident on the surface of one planet. Maybe the universe is not dead. Maybe it is mostly silent, because most life never builds a radio dish. Maybe the closest aliens, if they exist, are not watching us. Maybe they are drifting in black water under kilometers of ice, unaware that stars exist at all. That is a different kind of alien. Not an invader, not a visitor, not a civilization. A hidden metabolism in a sealed sea. And perhaps that is exactly what we should expect first. The first life on Earth was microbial. For most of Earth's history, life was microscopic. Complex animals arrived late. Technology arrived in the final instant of the planet's long story. If we use Earth as our only guide, then simple life should be easier than complex life. Microbial life should be more common than intelligence. So when we ask where alien life could be hiding, we are probably not asking where another version of us is hiding. We are asking where chemistry might have crossed the threshold into biology. That threshold may be quiet. It may not produce anything visible from orbit. It may leave behind patterns only a sensitive instrument can read. That is why the next generation of missions matters so much. Europa Clipper will not land on Europa or drill into its ocean, but it will study the moon in detail during repeated flybys. It will examine the ice shell, the surface composition, the magnetic environment, the possible exchange between ocean and surface, and the conditions that may support habitability. It is a mission designed not to find life directly, but to learn whether Europa is the kind of place where life could exist. That distinction matters. Habitability is not life. Habitability is the stage. Life is the actor. Before we can search properly, we have to know whether the stage is real. Future Enceladus missions, if approved and built, could go further. A dedicated plume sampler could carry instruments designed specifically to search for complex organics, cell-like structures, isotope patterns, and chemical disequilibria. It could fly through fresh plume material and ask questions Cassini could not answer. Future Mars missions may drill deeper than current rovers. The deeper we go, the better the chance of finding preserved organics shielded from radiation. If Mars ever had life, the best clues may be below the damaged surface, in ancient rocks or protected ice. Dragonfly will explore Titan's chemistry from the air and ground, moving from one site to another across an alien landscape. It will study how far prebiotic chemistry can go in Titan's environment, and whether the surface holds clues about the steps before life. Each mission is different. Together, they are part of the same search. And this search is not only outward, it also turns back toward Earth. To recognize alien life, we need to understand life here more deeply. We need to know how microbes survive in deep mines, under glaciers, in acidic lakes, in hydrothermal vents, inside rocks, and in frozen deserts. We need to understand how life preserves itself, how it changes minerals, how it leaves chemical fingerprints, and how those fingerprints can survive for billions of years. Earth is not just our home in this search, it is our training ground. Every extremophile expands the possible map. When we find organisms living without sunlight, icy moons become more interesting. When we find microbes surviving in Antarctic ice, Martian ice becomes more interesting. When we study hydrothermal vents, Enceladus and Europa become more interesting. When we study chemistry in salty lakes or acidic environments, we learn how to separate biological clues from harsh non-living chemistry. The more life surprises us on Earth, the harder it becomes to dismiss other worlds too quickly. But there is a danger in that. We can become too eager. We can start seeing life everywhere, and science has to resist that temptation. A harsh environment on Earth with microbes does not prove a harsh environment elsewhere has microbes. Similar ingredients do not guarantee the same outcome. Water does not automatically become biology. Organic molecules do not automatically become cells. Energy does not automatically become metabolism. The universe may be generous, or it may be selective. We do not know yet. That uncertainty is the heart of the video. The closest place alien life could be hiding is not a solved location on a map. It is a narrowing circle of possibilities. Mars is close enough to touch with robots. Europa is close enough to study repeatedly. Enceladus is generous enough to throw ocean material into space. Titan is strange enough to test the boundaries of life. Venus is close enough to remind us that atmosphere chemistry can be deceptive. The answer is moving toward us, but it has not arrived. And when it does arrive, it may not look like certainty at first. It may look like a measurement that scientists argue about. It may look like a pattern that needs another mission. It may look like a molecule that raises more questions than it answers. It may look like a tiny sample locked inside a sterile container on its way back to Earth. The discovery of alien life may not happen in one dramatic moment. It may happen slowly. A suspicious clue, a stronger clue, a better instrument, a cleaner sample, a second confirmation, a paper that survives criticism, a result that other teams cannot explain away. And then, quietly, humanity realizes the line has been crossed. That would be appropriate, because if alien life is hiding nearby, it has probably been hiding for billions of years. It does not owe us drama. It may not even know we exist. There is also a quiet emotional reason this matters. A nearby discovery would make the universe feel less abstract. We would not be talking about a distant dot around another star, too far away to ever touch. We would be talking about a place in the same family of worlds as Earth. The same sun would shine on it, however weakly. The same early solar system would have shaped it. The same gravity that arranged the planets would have placed that hiding place within reach of our machines. That would make alien life feel both stranger and more intimate. Not because it would be like us, because it would share the same neighborhood. It would mean that our solar system, which once seemed mostly barren beyond Earth, had more than one place where matter found a way to become biological, that would turn the planets and moons around us into something more than scenery. They would become chapters in a larger experiment that began when the sun was young and the worlds were still forming. So the search continues with machines that move carefully through impossible distances, with instruments that measure tiny differences, with scientists who spend years arguing over what a single molecule means. To some people that may sound slow, but this is how we approach a truth that large. We do not rush into it. We build the evidence, piece by piece. And in that slow work, the solar system begins to feel different. Mars is no longer only a red desert. Europa is no longer only an icy moon. Enceladus is no longer only a small object near Saturn. Titan is no longer only an orange dot. Venus is no longer only a failed Earth. Each one becomes a possible hiding place, not a promise, a possibility. And possibility is enough to change the way we look. Because the old idea was simple. Earth was alive, everything else was dead. The modern picture is more subtle. Earth is alive. Everything else is unknown. That word, unknown, is the reason we keep sending spacecraft. Unknown does not mean empty. Unknown does not mean alive. Unknown means the question is still open. And the open question may be closer than the stars. It may be under Mars. It may be under Europa. It may be in Titan's chemistry. It may be somewhere we have not thought to look carefully enough. For now, the closest alien life remains hidden behind uncertainty. But the hiding places are no longer imaginary. They have names. They have orbits. They have surfaces, atmospheres, ice shells, oceans, chemistry, and missions on the way. That is what makes this moment special. For most of human history, the question of life beyond Earth belonged to myth, philosophy, and speculation. People looked at the sky and wondered. They invented stories. They imagined beings on the moon, canals on Mars, civilizations in the stars. Now the question has changed shape. It has become measurable. We can send instruments to the places we once only imagined. We can detect water under ice. We can taste grains from a plume. We can map ancient lake beds on Mars. We can see methane lakes on Titan. We can plan missions not around fantasy, but around chemistry and physics. That does not make the question less magical. It makes it more real. The nearest alien life, if it exists, is not hiding in a story anymore. It is hiding in a place we can name. And that may be the most unsettling part, because when a mystery becomes reachable, it also becomes urgent. If life is there, we may be close to finding it. If life is not there, that answer matters too. A lifeless Mars, a lifeless Europa, a lifeless Enceladus, and a lifeless Titan would tell us something profound. It would suggest that even when planets and moons have water, chemistry, and energy, life may still be difficult. It would make Earth feel rarer. It would make our biosphere feel more fragile. It would make the silence of the universe heavier. That is why failure would not be meaningless. Every world we study narrows the possibilities. A negative result on one moon does not end the search, but it teaches us how demanding life may be. A positive result on one moon would expand the search forever. Either way, the solar system is teaching us, and the lesson is not finished. There is another layer to this that people often miss. Finding alien life is not only a question of where to look, it is also a question of how to look without damaging the answer. If a spacecraft lands on Mars carrying Earth microbes, then later finds something biological, the discovery becomes complicated immediately. Did the life come from Mars, or did we accidentally bring it there? If a mission samples an icy moon and introduces Earth organisms into a protected environment, we may not only confuse the science, we may contaminate a world that has been isolated for billions of years. This is why planetary protection matters. It can sound like a boring rulebook from the outside. Clean rooms, sterilization, trajectory planning, restrictions on where spacecraft can crash, careful handling of samples that return to Earth. But underneath those procedures is a simple idea. If there is life beyond Earth, we do not want to be the reason we can no longer recognize it. The spacecraft that search for life have to be treated almost like scientific witnesses. Every surface, every container, every drill, every collector, and every instrument must be controlled as carefully as possible. The cleaner the mission, the clearer the answer. This is especially important on Mars. Mars is the world we have visited most often. It is also the world where contamination risk is easiest to imagine. Earth and Mars are close enough that we have sent landers and rovers many times, and we may send humans there one day. But human missions are messy compared with robotic missions. Humans bring air, water, waste, skin cells, microbes, tools, suits, habitats, leaks, repairs, and accidents. A human footprint on Mars would be historically powerful. It would also make certain kinds of life detection harder. That does not mean humans should never go. It means the first truly sensitive astrobiology work may need to happen before large human activity begins, especially in places where liquid water or ice-rich environments could preserve life or biological evidence. Mars is close, but closeness creates responsibility. Europa and Enceladus create a different kind of concern. They may have oceans beneath ice. If those oceans are habitable, they are not just scientific targets. They are possible ecosystems. Even if they are lifeless, they are ancient chemical environments that have evolved separately from Earth for billions of years. A future mission that tries to land, melt, drill, or sample these worlds would have to be designed with extraordinary care. We would need to avoid carrying Earth biology into a place where it does not belong. We would need to avoid mistaking our own contamination for alien life. We would need to protect Earth too, if samples ever came back from a world that might contain unknown biology. The chances of dangerous alien microbes are probably not the same as science fiction imagines. Life that evolved in an ocean under Enceladus, if it exists, would not be adapted to humans. It would not know our bodies, our immune systems, our temperatures, or our chemistry as a habitat. But caution is not fear. Caution is how science remains clean when the stakes are high. The discovery of alien life would be too important to handle casually. This is one of the reasons the search may feel slow. We are not only trying to reach hidden places, we are trying to reach them correctly. The instrument that finds the answer must be sensitive enough to detect tiny traces, but careful enough not to create false ones. The mission must survive radiation, cold, distance, delay, and mechanical failure. It must send data across hundreds of millions or billions of kilometers. And then, after all of that, scientists must interpret the data without letting hope outrun evidence. That last part may be the hardest. Human beings are not neutral creatures. We want the answer to be yes. We want the universe to be alive. We want Earth to have neighbors. We want the long silence to contain hidden meaning. But the universe does not become more alive because we want it to be. A good search has to be disciplined enough to accept disappointment. This discipline is what separates astrobiology from mythology. It allows wonder without surrendering accuracy. It lets scientists say that Europa is promising, Enceladus is compelling, Titan is extraordinary, and Mars is important, while still saying that no confirmed life has been found. That balance is not weakness. It is the only way the final answer will matter. When we eventually claim a discovery, the evidence must be strong enough that the world can trust it. So what would strong evidence look like? It probably would not be one clue by itself. A single molecule would not be enough. A shape in a rock would not be enough. A change in gas concentration would not be enough. A tiny structure under a microscope might not be enough, because minerals and chemistry can create misleading shapes. Strong evidence would look like a pattern. It might be organic molecules, arranged in ways that strongly favor biological processes. It might be a set of isotope ratios that suggest metabolism. It might be complex molecular structures that form in a narrow range, rather than a random chemical mixture. It might be cell-like compartments found in a context where non-biological explanations fail. It might be chemical disequilibrium in an environment where living processes are the best explanation. Better still, it would be several of these together. In science, the strongest answers are often not single dramatic facts. They are networks of facts that support each other. Imagine a future Enceladus mission flying through a fresh plume. It collects ice grains that were inside the ocean only minutes or hours before. It finds salts, organics, and chemical energy sources. Then it finds complex molecules distributed in a way that does not resemble ordinary abiotic chemistry. It finds isotope ratios that hint at selective processing. It finds microscopic structures with consistent boundaries. It repeats the measurement on multiple flybys. Different instruments point toward the same interpretation. That would not be a movie moment. It would be better. It would be a scientific case. Or imagine a Mars sample returned to Earth from an ancient lakebed, collected deep enough to avoid surface destruction. Inside the rock, protected for billions of years, scientists find organic structures associated with minerals formed in water. The molecules show patterns that are difficult to explain without biology. The rock's history is understood. The contamination controls are clean. Multiple laboratories repeat the analysis. Again, not one clue, a case. Or imagine Europa Clipper, and later a lander, showing that surface materials are connected to the ocean below. A lander samples freshly exposed ice near a chaotic terrain or active region. It detects organics, salts, and patterns that suggest chemical cycling between ocean and rock. The results do not prove life immediately, but they identify exactly where a future mission should search more directly. That might be how the first answer comes. Not as a final revelation, but as a tightening circle. A place becomes more likely. Then a region becomes more likely. Then a sample becomes suspicious. Then a better sample becomes difficult to dismiss. This is why patience matters. The closest alien life could be hiding nearby and still require decades of careful work to confirm. That is not failure. That is what it means to ask a question across worlds. And there is another possibility that makes the whole search even stranger. What if we find life, but it is related to us? That sounds impossible at first. But Earth and Mars have exchanged rocks. Large impacts can blast material off a planet and send it into space. Some of that material can eventually land on another world. We have Martian meteorites on Earth. In principle, ancient microbes or organic material could have traveled inside rocks, protected from space for some period of time. This idea is called panspermia. It does not solve the origin of life. It only moves the starting point. But it matters, because if we find microbial life on Mars, one of the first questions will be whether it began independently or shares ancestry with Earth life. If Martian life uses the same basic molecular machinery as Earth life, the discovery would still be enormous, but the interpretation would become complicated. Did life begin on Earth and travel to Mars? Did it begin on Mars and travel to Earth? Did both worlds inherit life from somewhere else? Or did similar chemistry produce similar solutions independently? A second genesis is the phrase scientists use for life that began independently from Earth life. That would be the clearest proof that life can start more than once. Ocean worlds like Europa and Enceladus are especially interesting in this sense, because they are more isolated from Earth. It is harder, though not always impossible in every scenario, to imagine exchange of living material between Earth and a deep ocean under an icy shell around Jupiter or Saturn. If life were found there and had a biochemistry clearly different from Earth's, the case for an independent origin would be powerful. That is why the most important discovery may not simply be life, it may be unfamiliar life. Life that solves the same problems in different ways. A different genetic system, a different membrane structure, a different set of amino acids, a different handedness in molecules, a metabolism based on chemistry that does not fit Earth's patterns. Such a discovery would be breathtaking. It would tell us that life is not just a rare branch on one chemical tree, but something that can grow from different roots. But it would also make recognition harder. If alien life is too much like us, we have to ask whether it is related. If alien life is too different, we have to ask whether we can recognize it at all. This is the narrow path astrobiology has to walk. Search for the familiar enough to detect. Stay open to the unfamiliar enough not to miss. The closer the hiding place, the sharper that problem becomes. Because a nearby discovery would arrive not as an abstract idea, but as data on our screens, samples in our laboratories, and arguments in real time. The whole world would watch science struggle carefully toward the truth. And perhaps that is exactly how such a discovery should happen. Slowly enough that we understand it, carefully enough that we trust it, deeply enough that it changes more than a headline. So, where is the closest place alien life could be hiding? The most honest answer is this. It could be closer than the nearest star. It could be closer than any exoplanet. It could be inside our own solar system, concealed not by distance, but by ice, rock, haze, and chemistry. If we are speaking of distance, Mars remains the nearest serious place to search. If we are speaking of a present-day ocean with chemical energy, Enceladus and Europa may be stronger. If we are speaking of alien chemistry, unlike Earth, Titan may be the most provocative. But if we are speaking of the first place where we might truly catch life in the act, Enceladus may hold the most elegant clue. A hidden ocean that sends pieces of itself into space. That image is hard to ignore. Somewhere beyond the rings of Saturn, a small icy moon is leaking its interior into the darkness. Every plume is a message, but not a message written for us. It is only physics, pressure, fractures, water, ice, and chemistry. And yet, within those frozen grains, there may be information about an ocean no human eye has ever seen. That is the kind of place where alien life could hide. Not under a city of lights, not behind a signal from the stars, not in a place designed for human imagination, in a cold ocean under a small moon, where the evidence rises for a moment, freezes, and drifts away. Maybe there is nothing living there. Maybe the chemistry stops before biology begins. Maybe the ocean is active but sterile. Maybe every plume grain will tell us only that nature can build complexity without crossing the line into life. But maybe not. Maybe somewhere inside that dark water, chemistry has learned to maintain itself. Maybe tiny organisms cling to mineral surfaces near warm vents. Maybe they rise and fall with currents under the ice. Maybe traces of them are already being launched into space, waiting for the right instrument to recognize them. That possibility is enough to make Enceladus feel larger than it is. And it is enough to make the whole solar system feel less empty. Because the closest alien life, if it exists, may not be looking up at us. It may not know the sun as a star. It may not know the sky. It may not know planets, moons, or space. It may live in darkness inside a world we once considered frozen and dead. And if we find it, we will not only discover another organism, we will discover that Earth was not the only place where the universe became alive enough to notice itself. That is why the search continues. Not because we expect monsters, not because we expect civilizations waiting nearby, not because every strange moon must be alive, but because the ingredients are there, the hiding places are real, and the question is too important to leave unanswered. Somewhere close to home, under dust, ice, haze, or alien rain, the first answer may already be waiting. And when we finally find it, even if it is only one cell, the universe will no longer feel the same.